Welcome to third of our series in webinars on the subject of physical acoustics. Today I have a pleasure in introducing Dr. Hasina Begum, who is a research fellow in University of Warwick National Polymer Processing Centre. She obtained her PhD at the University of Sheffield. And now is, as I said, is a research fellow at University of Warwick. She's also active in physical acoustics special interest group and being the early career reps. And without further ado, I'll hand over the talk to her, and Hasina can start. Thank you.
Thank you, Shahram. And yes, hello and welcome everyone. It's great to be here and present some of my research that I was quite interested in during my PhD, and I also have some interest in it now. So today I will be presenting, the presentation will be on acoustic waves in hierarchical nanoporous materials, and the agenda is I'll just give a brief introduction about me and what I do and what my previous research has been. I'll then talk about my research in detail, and that includes some of the kind of new research that I'm doing at the minute at Warwick, which may not necessarily have a lot of acoustics in it, but there's still a little bit that I kind of tap into. And then I'll talk about the actual the presentation and nanoporous hierarchical nanoporous materials, and I'll talk about why those materials are important. I'll then go on to the current solutions and how we can kind of develop these materials and why they are great in society and what makes them applicable, and that will kind of lead us to a new solution. So a brief introduction about me. I did my bachelor's in chemistry at Manchester Metropolitan University, during which I worked for 2 industrial companies in between, and I had a very keen interest in polymers, which is why both my industrial kind of work that I did was all polymer related. The reason why I was so interested in polymers is because it fascinates me how one small unit can become a very long chain of something, and then it can be adaptable and applicable for many different things. And so I quite liked it in industry. However, I felt as though it wasn't very technically challenging for me. And so I decided that I'd like to do a PhD, and that was at the University of Sheffield. And that was in acoustics and sponsored by an industrial company called Armacell. So they were quite interested in manufacturing like foams and porous materials to be used for pipe insulation. So it was mostly pipe insulation. There was some building insulation as well. And I was quite fortunate enough that during my PhD, I got to work with lots of different institutes and collaborate both nationally and internationally. So the international ones were Materia Acustica in Italy, EMPA in Switzerland, and Purdue University and the University of Chile. But what I quite liked about my PhD was this idea of looking at porous materials, and how it wasn't just so when we take a porous material, we don't just look at it in its it's not all similar throughout the network. There are various sizes of this pore network. We call it hierarchical, and that was something that really fascinated me, and it was quite interesting to see the acoustic properties, and that's something that I'll talk about in this presentation. And then kind of just very quickly beyond my PhD, I stayed on and was part of the UK Acoustics Network, and that's still something that that is still a network that I work very closely with, and I do a lot of kind of EDI work with the UKAN network. I also went into industry, but then I didn't quite like it, so I went back into academia, and now I'm at the University of Warwick, where my role is more on polymers and sustainability and composites. Okay, so just kind of a very brief, just to give you some background. So my current research at the minute is I look at sorting of plastics using data-driven techniques. So I look at how we can sort them in an intelligent manner, and then use things like AI to intelligently sort the plastic. I thought this was quite nice to put in as a background, because it just kind of shows that it's not just porous materials that I look at. I look at various types of materials. I look at composites and different kind of polymeric structures, and it just gives you an idea of how these materials can be used for different applications. So that's kind of why this slide is here. I'll go on to my acoustics research now, because that's what this presentation is for. So in terms of acoustics, we want to understand the development of nanoporous materials to try and see what the microstructural and acoustical properties are. So I was quite interested in looking at silica aerogels and how we can develop and validate a robust mathematical model for vibroacoustic performance of composite insulation systems in pipes and buildings. So as you can see on the left, we have this aerogel material which looks invisible in your hand, and this is something that I was quite fortunate to make and have experience of making. And what was interesting about this material is that it has a very complicated pore network, and these pores consist of so we call it, so there are different terms, IUPAC terms. There's micro, meso, and macro scale. So micro is when you're looking at anything below 2 nanometers. Meso scale is anything between 2 and 50 nanometers, and then macro scale is 50 and above. Of course, the generic term is these are all nanoporous materials. So that's what I was interested in, and that's what I was looking at. So the objectives were to carry out a full microstructural and acoustical characterization of silica aerogel blankets that were manufactured by my company sponsors, Amacel. The idea was to look at the current materials and understand what the structure is, and then look at acoustic characterization, so using equipment like impedance tubes, and then using kind of mathematical models to predict the acoustical properties. It was also very important to synthesize new materials. So one key skill that I developed was it wasn't just a case of we were able to purchase commercial products. I was able to make these materials myself and then modify them myself. So change the pore size myself, almost like cooking, I guess. And then we applied, and then what we wanted to do was to apply a valid mathematical model to predict the acoustical properties. And then the fourth objective of the work was to support the material production and quality controls team at Amacel so that they can meet the industry standards for vibroacoustic and thermal insulation performance of their products. So as you can see on the left, we have, so this is how the material is supplied. This is the application for it, and it's supplied in a blanket form, and it's embedded in a glass fiber matrix. Now, the reason behind that is because these materials are incredibly fragile, and they break very easily. And that's why it's really important to incorporate them within some kind of matrix or glass fiber or fibrous network. And the way in which that is done is actually mechanically impregnated. The images that you see on the top are SEM images, and these images just show what the material looks like in its, we call it monolithic form, so it's kind of intact structure. So on the left of the SEM, you can see the aerogel as a powder embedded within the fiberglass matrix. And then on the right, you can see the aerogel in a more zoomed in picture, which is with a 50 micron scale bar. And you can see, maybe it's not as clear on the slideshow, but there are actually very small holes or pores within the structure, all around the structure. And it's because of these pores that we see very strange or interesting behavior when we introduce an acoustic wave through the material. So in terms of the testing procedure, as I mentioned earlier, these materials were tested or looked at using impedance tubes. So using a standing wave tube, and you can see that there are two kind of upright tubes. And the reason they're like that is because a lot of the material was supplied in powder or granular form, and the tubes were quite bespoke tubes, so we were able to fit 50 cubic centimeters of the sample, but it had a diameter of 10 millimeters, so it wasn't very big. And if I show you there's a nice kind of video here where you can see how I tried to insert these materials. So it's very difficult to take this material out, so I just use some dental floss. But you can see I was quite interested in looking at the monolithic form, so the shape, the structure in its physical kind of 3D shape, and I was also interested in the powder or granular form, because we found that when we started to change the physical properties of the actual physical nature of the material, again, we saw strange behavior. We actually saw more resonance behavior, and that's something I'll talk about. So why are porous materials important? Well, they maximize energy generation and they improve on storage. Porous materials in the millimeter size are very common, and they are useful to hold large volumes of liquid within its cavity. And that's because when you granulate a material, or when you turn it into a powder, effectively you're increasing the surface area. So, and that is why that's one of the reasons why it's useful to hold large volumes of things within the material. Here it says large volumes of liquid because the material itself is very porous. So it has these pockets, which allows it to hold large volumes of liquid. The pores in the nanometer scale are actually 6 orders of magnitude less, and they enhance the properties that we wish to exploit of a material. Also, the pore volume, the pore size, and the surface area of these particular materials, they define the texture of the solid, and it is in this empty space within the material that a wide variety of physical and chemical processes take place. So as I mentioned earlier, surface area is a big factor, pore volume and pore size, and that's because you have these structures and they have these pockets or cavities. What happens is when you're initiating some kind of acoustic wave, it's bouncing between the kind of voids in the material, and it's not going through one straight path. And that's why these materials are of great interest, because we see some very interesting behavior in terms of physical and chemical properties. And another reason why porous materials are important is that it allows us to increase the storage capacity for new material application. And again, that's because of the actual porous nature of the material and the surface area of the material. So the applications of these materials, well, they are highly efficient absorbents and membranes, and they reduce energy consumption and waste separation. They allow absorption of toxic substances in biomedicine. So another good thing about, well, in particular, I was looking at silica aerogel. Another good thing about these materials is that they are hydrophobic. So, and what that means is that it's water hating. So when you have a material that's hydrophobic or has a high adsorption, it means that anything that is attracted to the surface of the material, we call it adsorb, because this all happens at the surface. It adsorbs everything on the surface, and so nothing is able to actually be absorbed within the material. And this is really, really beneficial for if we wanted to use these materials in applications like biomedicine, to prevent things like toxic substances from entering the body. They're also great as catalysts for chemical reactions in the pharmaceutical industry. Now, what we mean by this is catalysts they initiate chemical reactions. Now, because porous materials such as silica aerogels they have such a large pore space and they have such a large surface area, this allows more reaction to take place. And that's why we say they are good to be used as catalysts. The adsorption and the separation of gases is of great industrial interest. Now, what we mean by this is these materials, because of their porous nature and the kind of interconnected pores that they have. So one thing that I didn't mention is the pores within materials like silica aerogels it's an open pore network. So so when we have adsorption or separation of gases occurring, it happens within these cavities, and that's something that's really important for industry, because they don't want the sound waves or whatever application they're using the material for to just bounce against the pores and kind of bounce back. They would like the material to, they would like the sound waves to be attenuated through the entire material and kind of be absorbed in that way, and that's why these are of particular interest. The final application is energy storage field. So when we look at materials like activated carbons in electrodes for supercapacitors, which due to their low cost and large surface area, they allow specific capacitance. So what we mean by this is not only are we interested in silica aerogels, materials like activated carbons are also quite interesting because of their very porous nature, and it's these materials that allow us to kind of see how they behave because they have large surface areas and they allow that high specific capacitance. On the right here, you'll see a table which gives you some examples of porous materials and their respective surface area values. And this just gives you an idea of kind of the difference between activated carbons, silicas, zeolites, and MOFs, metal organic frameworks. So you can see that silica aerogels are quite in the middle in terms of surface area that's highly wanted in industry. Activated carbon is a material that's highly required in industry because of its large surface area and the different applications that we can utilize it for. So with this, you're probably asking, well, okay, so we have all these porous materials, nanoporous materials, but how are we going to understand the pore structure? How are we going to understand what happens between each pores without destroying the pore network? So what we'd like to do is we'd like to combine the techniques that are currently available. So as I mentioned before, when we talk about nanoporous materials, we're effectively talking about microporous, mesoporous, and macroporous structures. You can see in the middle part of this diagram, there are different types of materials, so activated carbons, mesoporous silica, cellulose aerogels, silica foam, and you can see how the pore structure changes across. So we have activated carbon, which has pores as low as 1 nanometer, but then you have things like polypropylene foam, where the pores are around 10 micrometers. And currently, the way in which we analyze these pores is through various different techniques. So we have things like wax, which is wide angle X-ray scattering, SAPS, TEM, BET, transmission electron microscopy. BET is a type of technique that allows us to understand. So the way in which we use BET is we fill pores with nitrogen and we allow nitrogen to be adsorbed onto the surface, and then we kind of empty the pores out, and then based on different calculations, we're able to calculate pore size and pore volume. Now you can see with all these different techniques, there are limitations with the range of the pore size that we can analyze, and that's not good enough, because when we're looking at materials like silica aerogels, which have hierarchical porous, which have a hierarchical porous structure, we want to be able to characterize the entire pore range, right from the 1 nanometer right to 10 microns. And so how do we do this? How are we able to analyze the size of the pores or the pore structure of hierarchical porous materials using a non-invasive technique, such as acoustics. And so this is where I'd like to, and if anyone has any ideas, then please let me know. But this is where we come up with the idea of, we'd like to measure the structure of nanoscale porous material with non-invasive means. So we want to actively probe them with sound waves at the audible frequency range under different fluidic environments like helium and nitrogen and carbon dioxide, using different pressures, different temperatures to unravel the acoustic signature of the adsorption and transport it in hierarchical materials. What this will allow us to do is it will generate a large systematic data set on the structural properties of these hierarchical porous materials, which will then be combined with a physics-based inversion modeling to establish acoustic measurements as a tool for structure determination and enhanced material applications for energy storage. So by generating this large data set, we will then be able to understand, well, how we can create materials with certain pore sizes for specific applications. And then what this will do is it will provide us with an open access database, which will eventually be available, and we can start using things like machine learning algorithms to generate more data and use for future applications. So that's kind of the idea. So what is the solution then? Well, the solution here is we have an impedance tube, and the impedance tube has your two speakers with a loudspeaker, and we'd have a gas inlet. The gas inlet would have different types of gases available, which will be different types of gases such as helium, argon, carbon dioxide, krypton even. You'll find that these different gases have different, they increase in size. So the molecules of the gases increase in size because when you have a small pore structure, you need to use gases with smaller molecules like helium. When you have a bigger pore structure, you need to use larger gases like krypton. And the reason behind this is because we want to fill the pores. So we'd have this through a gas inlet, and then we would use various different porous material samples like activated carbon or aerogel. And this would allow us to understand the impedance tube measurement, look at using some kind of inversion method, which would then generate data on what the pore structure is, what the pore size is. And then from this, we can generate more data, use machine learning, and be able to characterize the pores better. And then in the future, we could say, well, if we have a material with this type of pore structure or with this size of pore structure, this will be good for certain applications like energy storage or biomedical applications and things like that. And so that's kind of the idea. And what I would be very interested is if anyone has any advice or any kind of understanding on how this can be done practically. Can it be done practically? Is there particular materials that I haven't looked at? Is there a particular type of equipment or analysis that I haven't maybe considered that will allow me to characterize pore structures in an effective manner? So I'd just like to acknowledge a few kind of institutions, people, organizations that have helped with understanding this project or have helped me along the way. And that was University of Sheffield, my industry sponsors, Armacell, the companies and organizations that I collaborated with, UK Acoustics Network, and my current university, Warwick University, for giving me the opportunity to present as part of UKAN+. Thank you very much.
Thank you very much, Hasina. We have plenty of time for questions, and let me see if I can. We already have two people asking questions. And Keith Attenborough says, why restrict to audio frequencies since use of ultrasonic frequencies is well established for determining physical properties such as tortuosity and characteristic lengths? Keith, do you want to make the point yourself?
Yes, hello. Am I unmuted?
You are unmuted and we can hear you. Thank you, Keith.
Yes, sorry. It was just a passing reference. Hasina mentioned that she was going to use audible frequencies. So I just wondered why restrict to audible frequencies, since in the past, when characterizing porous materials, there's been quite a lot of use of ultrasonic frequencies too.
So the reason why it was restricted to audio frequencies, because from my understanding, the impedance tube can only look at a specific range of frequencies. I'd love to look at a much larger frequency range, but from what I understand is the smaller the impedance tube becomes, the larger the frequency range, and there's only so small that we can go unless I'm not aware of a particular technique that's available.
Yes, I think that even the standard impedance tube is 10 millimeter size cross section, internal cross section. Is that right? No, 10.
Yeah,
10 centimeter. Sorry,
is,
10 centimeter. Yes.
Yeah. The standard is 100. Yeah.
So, but I mean, I think people have even used 3 centimeter cross section impedance tubes to do measurements. Even if you can't get to really high frequencies, you can look at the trend, the high frequency trend, and extrapolate to find out various parameters. I think that's been done in the past.
Okay. Is there a particular technique is there an experimental, because I'm more of an experimentalist. So I know that, you could extrapolate, but is there an experimental technique that I could use which would allow me to look at a larger frequency range? Because I would be interested in that.
Well, I think you should look at the papers by Philippe Leclerc. I think he's probably the most important exponent of how to do this kind of measurements. But also, Kirill will know about these methods.
Okay. Yeah. No. I'll thank you for that. Yes. Sure.
Can I interject here? I think I can see a couple of issues with. Yes, it can be used, but for example, the depth of penetration might be an issue if the material is dense enough for high frequencies. Of course, you can't use very high frequencies in an impedance tube because the principle of plane wave propagation breaks down and we get into multiple modes. So a different technique altogether needs to be done and needs to be achieved. And there are sensors which can be coupled into the surface of the material directly and reflections measured. But it's worth investigating. Yes, Keith is quite right. Thanks.
Yes.
Yes, there is a paper by Fella-Berger, Lorix et al. Is in the chats. Someone helpfully put the tortuosity of porous materials via reflected waves at oblique incidence. Thank you.
Thank you.
Great. Any other questions? I can't think of any. Oh, is there more?
Thank you.
Thank you. Yeah, thank you.
I'd be interested to turn this into some kind of opportunity to as another research project, or maybe find a way to turn it into another research project of some kind. So I'll have a look at that paper and then see if I can develop it further. And yeah.
Right. Well, thank you, Mr. Begum and Keith Attenborough for suggestions of paper. Is there? Oh yes, there's more coming. Oh, that's great. Thank you. They say there's gear available in Lyon, and if you wish to contact them, that'd be good. Thanks very much for that.
Thank you.
That is very useful.
I will get in touch once I'll be.
Yeah.
Thank you. No problem.
I can't think of any questions. If there are no further questions,
Sharam, wait. Sorry, I forgot to unmute Francois. Yeah, you can now talk. It's the microphone is available.
you need to unmute him, Anton.
Yeah, hello, good afternoon. Good afternoon, Hasina. Good to see you. Now, just to say that we have the this gear available for measuring the tortuosity. If you think that can help, we'd be happy to help with the project if needed.
Okay. Yeah, no, I will. I'll get in touch because this was actually a proposal that I wanted to write about. So anything that I can talk about that will strengthen it would really help. So I'll get in touch with you separately. Thank you.
Okay, good, excellent. Thanks again.
Certainly, it can be a very powerful tool in sensing, determining properties of nanoporous materials. Any other question? Well, if not, then thank you very much, Hasina, for your interesting presentation, and thank you for to our audience for joining us. And there will be another webinar to be arranged by Dr. Giyawa Usaro in mid to late July, and we'll make the announcement in the usual place in UKAN website on the Physical Acoustic SIG. And with that, I thank you all and wish you good day.
Thanks very much, Hasina. All the best.
Thank you. Bye.
Bye.